Hello everyone, welcome to the second session of the QFT. We are going to talk about Klein-Gordon field today. It is the simplest particle, or it's the simplest field that can be written in two types, real valued and complex valued. So Klein-Gordon field can be real or complex. And the real one is basically explaining in a spinless particle. And we are going to talk about the symmetry on those types of fields, which is going to be energy momentum conservation. We're going to use Noether's theorem to derive this conservation. So Noether's theorem somehow making a link between symmetries and the conserved quantum charges, and the complex field explaining somehow charged particle. And we're going to talk about how this charged particle is similar to electrical charged particle, but by only having one scalar field we cannot explain electromagnetism. We're going to see we have to introduce fermions and then photons to somehow construct the correct version of electromagnetism, but something similar to electromagnetism can be seen in this context of complex Klein-Gordon field and basically the U1 symmetry. So the title is how U1 symmetry is somehow leading into a conservation of charges and similar to electrical charges. So because this U1 symmetry is gonna see here, it's a kind of introduction to the U1 symmetry in electrodynamic or quantum electrodynamic. So in general, this U1 represent the gauge fields or types of interaction, which is going to be electromagnetism, U1, and then we have SU2. So we are just seeing that the mathematical dimension is just going up by 1, but we don't have to forget that these are about complex number. We are at least talking about the space of the matrices that are filled with complex numbers. So the dimension of them is somehow doubled of the dimension that we think, because there are two components for the complex number. But however, this SU2 correspond to weak interaction, and then we have this SU3 that carries the strong interaction or quarks and gluon interaction. And we're gonna somehow starting from something very simple, Klein-Gordon. So Klein-Gordon field is basically can be Higgs particle, because Higgs is the only basically scalar particle in the elementary standard table. So in the standard model, we're gonna see there is only one particle that it is like a scalar, and that's Higgs, that somehow couples to every particle and gives them the mass. But Klein-Gordon field historically is an approach from one particle. So historically, if we don't want to think about now we are living in this time, we are living at some time ago, and we want to see it was some one particle quantum, let's say quantum one particle. We talk about this quantum one particle, that when you have one particle and you have a Hamiltonian, you can in general quantize it, and then when you quantize it, find the eigenstates of the energy. So this quantum one particle, when we write down the case of relativistic, so when we do relativistic correction, which is just simply Hamiltonian squared is equal to p squared plus m squared, then we're going to see this is Klein-Gordon from the historical point, but from the context of what we learn later on, Klein-Gordon field is somehow very simple field. It is somehow a toy model, right? We don't want to say it's a toy model, but it is representing something very simple. And then later on, people realize, okay, if there is such a particle, it should be something that gives everything mass, because of the scalar nature of them. We're going to realize that fermions have some degrees of freedom inside of themselves. So they have a spin and other characteristics that are like vector characteristics make other particles not to be a scalar type. So we need some scalar particle, and Higgs can be seen like that. However, if we just want to look at it from the point of mathematics, the Lagrangian is starting with some kinetic term. So I don't want to call it kinetic energy because this is not kinetic energy. And the kinetic energy, it is somehow similar to kinetic energy, but the difference is the Lorentzian signature. So if we think about the Lorentz signature of the energy, the space component of the energy and the time component of the energy should be added to give us the energy. So energy is something positively well defined. But the Lagrangian, we have this Lorentzian signature, and then we have this T of which is the function of the first derivative of the field. So we treat this derivative of the field independently from the value of the field. So we say the Lagrangian somehow depends on phi and the first derivative of the field. And again, we didn't see an example of in physics that the Lagrangian depends on the second derivative of the field. Somehow the nature is well behaved. However, we can think of it as in the Lagrange and Hamilton formulation. If you think about that, you have some equation of motion, and if you satisfy certain boundary condition, and when you're talking about boundary condition, you have two options: to know the initial location and initial momentum, or to know the initial state and final state. So we said in the Hamiltonian formulation, we think of initial boundary condition, knowing momentum and the initial location is sufficient to determine one well-defined differential a function which can be differentiated, and it is unique. So that exists uniquely can be seen as the answer of equations of motion. However, we just want to say that knowing two value of the field and somehow first derivative, which could be seen as momentums, are sufficient to have information about the physics. So we have this T kinetic term minus this potential term V, which is a function of phi, basically. So now if we think about it, the first thing that comes into our hand is that when we have this value of the field and we do the first transformation, and transformation is something arbitrary that we are doing it. So the physics of the physics of the system should not depend on the way we labeling and coordinating a field value. So it doesn't really matter if I change the value of the field to the negative of itself. That shouldn't change the physics of it. So how can I encode into the physics? The physics is Lagrangian. So when I talk about physics, maybe I have to say this correspondence is direct correspondence here between physics and Lagrangian. So in general, Lagrangian is a scalar. So the definition of Lagrangian is something is scalar. That means that it doesn't depend on the way we label the coordinate, or on the other words, if we do certain transformation, the Lagrangian doesn't change. And one of those transformations, the very basic one where we can think of it, is that the Lagrangian should not depend on the value of the field and the odd powers of the value of the field. So if I think about this potential term here, and imagine I can expand this potential term based on some phi and phi squared and phi 3 and so on, and imagine they have all this coefficient here, epsilon 1 and epsilon 2 and so on. And it doesn't even need to be very perturbative here. I mean, those coefficients can be like normal. But again, those terms with the odd powers cannot survive, because when phi goes to minus phi, the value of the Lagrangian change. So we have to get rid of them. And this is like an imposing symmetry into a Lagrangian. And if you think about it, always, from the perspective of Greek philosophers, we somehow say nature should respect certain symmetries. Not only we think of them as they're beautiful or something, but the first logic of it is that the physics is not should not depend on the way we label and coordinate things. So coordination and labeling things is something that we do, and we have to say this is the description that we make from the system, but the system is somehow governed by itself, and the physics inside of it should be independent. That's how we write down these scalars. The scalars are preserving this property that it should be somehow some symmetries. And this t of phi is some derivative terms and their powers. So it could be second powers and so on, and we have to get rid of the odd powers 1 and 3 and 5 and keep the even powers. So now you just have to write down this Lagrangian here. So this Lagrangian is have to be in a scalar, right? One way to make a scalar is to do inner product. We have to do inner product or internal dot, internal projection. There's so many things in quantum. Basically, bracketing is somehow inner product, and the way we construct some Lagrangian is also inner product. So we have this Lorentzian, we have this Einsteinian signature that we use covariant and contravariant component of the vectors. You know, covariant and contravariant are similar to operation in dual space. So if you have one operation on the first space, let's say this one, and then you have another operation on the other one, so then you bring them together, it is like an inner product minus some factor 1/2 is basically that we have this second power here. And the mass term, our potential term, is somehow we see the mass is appearing here. So this mass is like a coefficient here. It is somehow can be seen as the resistance of the field to gain the energy. So imagine if I have some available energy. Imagine that I have some available energy. Let's say I have V amount of energy, and V is equal to 1/2, let's say proportional to -1/m squared phi squared. So the value of the field is proportional, let's say, to V divided by m squared. So that means that if a particle have a lower mass, it is easy to make a lot of them. It's very trivial, you know, but again, we are translating everything to the field description. So, I mean, when we are talking about particles, we are going to see how second quantization or how these fields are going to be quantized. It is not, we are not yet there, but we are going to just talk about classical field. If we are thinking about classical fields as coarse-grained or averaged value of the field that gives us a statistical description of the system, then imagine this is a space-time and this is phi, and imagine if I have one available energy, imagine that if I have some energy and if I have two fields, and if I call them M1 and M2, and if I have same amount of energy, that necessarily means M2 is larger than M1. So if we have high mass, the field tends to go to zero if we have certain amount of fixed energy. So it's just a classical interpretation. And this is something very trivial. So we write down Lagrangian, but we want to say how this Euler-Lagrange equation is, the Euler-Lagrange equation is somehow derived. Maybe it's like a review for many of you who maybe had some problem with it like me. So I really didn't understand what's the meaning of this. Oh, before I go to the variation technique, let me just say, let me just stop in this first derivative or the second derivative of the field and the value of the field. And we can say, why can't we go to the higher terms, terms with higher power? And this is somehow possible. When we're talking about renormalization, we are going to talk about how can we effectively compactify all the terms into one effective coupling constant. We still didn't say anything about coupling constant. But in general, we are just keeping the lowest order of these expansions, which is just the second terms, for the potential and for the kinetic part. And we are going to see how this is going to be. So it is still legitimate to ask, why can't we have higher terms, higher power terms? We are going to see it later. What's the connection into coupling constants? So now the Euler-Lagrange equation are what? Euler-Lagrange equations are differential equations that are satisfied by one particular trajectory or path, which we call it the minimum action. So we want to find what's the minimum, what path is the minimum action, and we, in classical physics, we say that path or that trajectory is somehow the physical trajectory that has the minimum action, so minimum S. So the idea is that if I'm in the functional space of imagine that I'm in the functional space of phi. Imagine that there are all possible phi that could exist at the same time. And imagine I go to this functional space and I find a phi which has the minimum action. And the assumption is that I'm going to find this path. So somehow it is guaranteed from if S and all those Lagrangian functions are analytic function of phi, and analytic means that it is analytic in all the points or the domain of those functions, then there must be a trajectory with the minimum action. And the mathematics of it is somehow simple and dumb in physics, but it is just very interesting. So let's say I have this delta operation. So this delta operation is not something very well defined. I'm going to show it to you that this delta operation can be seen as alpha plus some phi plus some alpha delta phi, and I would call this so this alpha means this phi is the value of the field, so it's the original value of the field, and this alpha is the infinitesimal parameter, and this delta phi is deformation. The deformation of the field is any arbitrary deformation. So this delta phi, for example, can be proportional to phi, or delta phi can be proportional to the derivative of the phi. And we're going to see this is, for example, for the case of a space-time symmetry, and this phi is just for the case of electrical charges and U1 symmetry. But however, this delta means that I do a variation over phi. That means that I just go around the phi with the minimum action and I do some variation. So the idea is that if I'm around that phi, around that phi of xt, which has the minimum action, so I would just write down these labels on it. If I have delta phi, my delta Lagrangian should be 0, which means my Lagrangian should be at the extremum points of those functions. So again, this is imagine the phi, and this is xt, and this is I and f, initial and final. Imagine these are all trajectories that are allowed. So I just want to see how to derive this Euler-Lagrange equation from this principle. That if I use delta phi, the delta Lagrangian is 0. So I say the Lagrangian is a function of two independent terms. So delta of Lagrangian can be expanded by the derivative of the Lagrangian with respect to phi, and delta phi, I'm just like breaking Lagrangian into the independent terms, and this is coming from the assumption that I can use the derivative of those terms and then multiply them into the delta of. So here I just have I'm trying to write down the delta operation of L or Lagrangian as delta phi and delta of the derivative of the phi. And these two are different. We're going to see these are two, again, independent. We have to treat them independently. And then we have something like that. We can expand this Lagrangian like this. And now we want to see if I put it equal to 0. Well, we're going to see why am I going to put it equal to 0, not now. But let me say, so now I say S, or the total action, is equal to the integral of Lagrangian of phi and derivative of the phi over what? Over the 4-dimensional spacetime. Imagine I put the dimension 4 for a spacetime. So I say the delta of action is equal to 0 because we said it's about action. And then delta S is going to be delta L d4x equal to 0. So now we have an integral equation. So when an integral equation is equal to 0, if we say now the inside of the integral should be equal to 0, so it can be satisfied all the time, independent of everything else. So now the integral of delta Lagrangian, d4x, is equal to the derivative that we wrote, delta phi plus the derivative of Lagrangian with respect to the field, delta of the derivative of the field, d4x, is equal to 0. And now I just want to how to deal with this delta of the derivative of the field. So now we want to talk about if I have delta phi and if I have that, how can I just write everything in terms of delta phi? Because again, that's the simplest term. We are trying to factor it out, right? We are trying to factor it out, take it out, and write down all the equation equal to 0, and then inside of that is equal to 0. Why? Because we are talking about any variation with respect to this field. So we are talking about this integral. Imagine you say this integral d4x is going to be equal to 0. That means you have something here, delta phi d4x is equal to 0. And let's say, because I had any type of arbitrary deformation, any arbitrary variation of the field, then this should be equal to 0. So this is what we want. So now we go down. So, I just say the delta of mu phi, it can be written as the derivative delta phi. So it might not be seem very trivial here that there is such a relationship, but if we think about both of the operation as some linear operators, they can commute. This is something in quantum mechanics, similar to quantum mechanics. Can we commute two operations on the same field? And here, because both of those operations are linear and somehow real value, or even like they are not in a kind of higher dimensionality, they are talking about complex values and real values, they can all commute in a form. Again, delta is somehow can be seen as some value of the field is add to some infinitesimal parameters. So it is linear to some term, and I can commute them. Okay, so now delta S, go back to that. Delta S can be seen as this following terms. Okay, so now what's the problem here? I want to take out this delta phi, but this delta phi is under this derivative here. So this derivative is protecting what's inside of the parentheses. So to do that, I'm just going to do a trick. I'm just going to do a trick. I'm writing it down as something like this. It's just very simple algebra. So I say this expression is equal to the derivative of the whole thing minus that term that doesn't exist in the original form. So there we don't have such a thing. We just have to subtract it down. So now we took out this derivative from the whole thing, so we can deal with this term. We're going to see how is it related. And then, okay, so now I'm trying to rewrite the expression. So delta S is going to be the integral So the first term is there, right? The first term is there. So the second term is going to be as we rewrote it. A full derivative of something inside of the parentheses, which consists of two terms, the derivative of Lagrangian with respect to the derivative of the field, times delta phi minus the space derivative of this term. We're going to see this can be seen as momentum. What's inside is somehow similar to momentum. So you're talking about the derivative of momentum times delta phi. And now we have what we want to have. So we have these two terms with delta phi. So look at these two red one. If you look at these two red one, they have what we want, right? So we can somehow write it down as one big delta phi outside and just inside subtract. Right? And then we have this extra term. Now let me just separate this term from the rest of them, because that's an easy term to handle. What is that? It is a full derivative of something. So when we are taking integrals from the full derivative, the things comes out without the derivative. So this comes out without derivative. So this integral can be evaluated. And this integral is also what we're going to see. So we want to put the whole thing equal to 0. So this is equal to, imagine the first part, d for x, plus the second part. So now for the second part, I just take the derivative out. So I just take this derivative out, and I just write down the function inside. And then what? I subtract the final from initial, right? And now we use this trick. The trick was any variation was 0 at the end point of initial and final state. So all of those deformation, delta phi at final is 0, delta phi at initial is 0. So this term is 0. Now, essentially, the first term should be equal to 0 in order to hold the equation. And what's inside should be equal to 0. So that just simply giving us Euler-Lagrange equation. It's a very beautiful differential equation that gives us the ground state, or let's say a minimum action, let's say. It is somehow related to ground state, but it is not the ground state. Anyway, so I have this Euler-Lagrange equation. I can write down an equation of motion. Equation of motion is a wave equation. So when I'm talking about wave equation, I'm talking about somehow wave function. So we previously talked about quantum field theory is a framework which allows you to go beyond one particle. But if you think about the particle as one rigid classical particle, then you can write down the wave function. This wave function is going to be meeting this quantum field theory, but only in that level. So the first term here, so I'm just like writing down the equation of motion. The first derivative of the field is minus m squared phi minus the derivative of Lagrangian with respect to the derivative of the field equal to 0. So this term can be evaluated, and it could be as the muth derivative of the phi. Or let's say we have to really be careful about the covariant and contravariant. So here it's the lower case here, and then it is on the denominator. So when it comes up, it would be an uppercase. So I should put it like uppercase. Okay. So now the equations of motion turns out to be minus equal to 0. And now if I take everything on one side, it would be, oh, there's a phi here, sorry, m squared phi is equal to 0. And then I can write it down as this form. I can write down this as an operator form. And I would call this term box squared. And this box is basically a time derivative minus a space derivative. And it's a Lorentzian signature. So now this equation is called Klein-Gordon equation. Right? And we're going to show this is going to be one particle wave function. So one particle wave function, which is psi x squared dx, or let's say d3 of x, is equal to 1. d4 of x, even. So this is, we are talking about a wave function. So instead of state psi, I'm just going to use the phrase state phi. And the relativistic particle Hamiltonian is h squared plus p squared is equal to p squared plus m squared. Now I go to Schrödinger equation, right? So Schrödinger equation is stating that the Hamiltonian acting on the state is equal to I, the time derivative of the field. So we know, because we are dealing with Hamiltonian squared, let's act this Hamiltonian again. So Hamiltonian a squared operator of phi is equal to I squared, the second derivative of the phi. And then I project it on the x, right? I'm talking about, again, one particle. And then I take this Hamiltonian up here. So I ended up with two terms here. Some p squared terms, some m squared terms. So this m squared is basically identity operator times m squared. M is a scalar. And then I have I, which is going to be minus 1, second derivative of phi. And there is this x, projection on x. And from quantum mechanics, we know that this term here, if we have a momentum term and then we have projecting it on the x term, we are going to ending up with something like I squared, because again, one I is coming out. So this is the art of this imaginary number. And then it would ending up with the second derivative with respect to a space. Well, we are talking about p squared. We are talking about px squared plus py squared plus pz squared. Now we are just thinking about all independent and similar. So we are talking about, we can reduce it always to one dimension and then easily generalize it in the 3 dimension by just a coefficient. So now this would be the phi of x. So phi of x is what? Phi of x is phi on x, right? So plus m squared phi x is equal to the second derivative of phi x. Now, if we are just like bringing everything to one side again, and this I squared term is also going to be minus here, the Lorentzian signature is respected because the time component is going to be on the other side positive, and then we have this space component negative, and then we have this m squared and phi squared. Now, okay, so we just showed the Klein-Gordon is just simply one particle Schrödinger equation, and let's go to the Noether's theorem. Noether's theorem. It's a very beautiful theory in classical field theory, connecting symmetry into conserved currents. Well, let's say currents carry charges. So the word currents and charges are somehow equivalent to each other. And it's just integrating everything together. So if we, again, historically want to talk about it, from the historic point of view, the conservation of electrical charges was not something trivial, and concluded from some fundamental symmetries, like again, the energy and momentum conservation was correlated to the translation in space and time. So the momentum is trivial to see the space homogeneity or space symmetry. But how electrical charges can be explained by some value of the field or some inner structure of the field was not something well understood, which then realized by this theory. So the theorem is saying, okay, if I take phi to phi plus delta phi, okay, and let's say this phi is infinitesimal. I have to assume that this is infinitesimal. So this phi is going to be alpha delta phi. And the reason this is infinitesimal is because I have to be able to turn it off. So I have to look at it at the vicinity of the point. So infinitesimal parameters allowing us to go to the first orders by somehow converging into one point. So the mathematical argument of this is something very interesting in general courses of mathematics, that how can you converge. But however, everything should be local and infinitesimal. And we're going to see how the locality and globality here are acting a law in the conservation. So now if I have this, imagine that I have this transformation. So I take one field and deform it. Well, let's say I take one field and add alpha delta of the phi or some deformation. My Lagrangian is going to be Lagrangian plus some Lagrangian deformation, right? And if I can write down this Lagrangian deformation, the deformation of Lagrangian, as the full derivative of some function, which I have to find out. So this is like integration. I see a function, I have to think of it as a function which can be rewritten as the full derivative of another function. That would be the derivative of Lagrangian. So there are two possibilities here, is that the deformation in the Lagrangian is 0. So that's the first option. And the second option is that the deformation of the Lagrangian can be expressed in terms of some function with full derivative. So this is something that we are putting it by hand. If this happened, if this situation happened, then I would construct another field from the original field, and that field is the charges or the currents, basically. If I have my imagine phi field, and if I have a Lagrangian which respects certain symmetries, so this Lagrangian here is sitting on top, then it would allow me to take some j function, and I say this j mu, it's a vector function. So even if I start with a scalar particle, I would, this Lagrangian inducing this j function that carries the electrical charges. And when we say it is conserved, that means the full derivative is equal to 0. Okay, so I mean, if I have this imagine phi here, then I would have something blue, which is going to be j mu. Okay, so now I just want to prove how to construct. So I mean, sometimes to prove something, you need to construct it, and then you say, this is the way I construct it, and then this is how to explain it. I mean, how to be proven. Many mathematical proof is something similar to that. So imagine I assume the general case here. General case is, imagine I write down the deformation in the Lagrangian as some infinitesimal parameter times the full derivative of some j mu. And imagine I have to find out this j mu. And this is the algebra that we need to do. So to find it out, need to do algebra. Okay, and we're gonna give an example of it. It's very fun. So then I know the deformation of the Lagrangian can be written. We just write it down for the proving the Euler-Lagrange equation. So we have this Euler-Lagrange equation term. So the deformation, imagine I want to write down everything in terms of the field deformation. Okay, so now imagine this delta Lagrangian is equal to the same alpha, the full derivative of some j mu, right? And just think about the first term. It's the Euler-Lagrange equation. So this is equal to 0, right? Because it already, the coefficient inside is 0, so everything is 0. Now I ended up with something like this. So I will have alpha, the infinitesimal parameters, full derivative function is equal to minus the derivative of Lagrangian with respect to the derivative of the field delta phi. So this whole delta phi is inside of the parentheses. So we are taking derivative on both of them, okay? And again, we start with the assumption that delta phi is equal to phi plus some infinitesimal parameters delta phi. And imagine this delta phi is something that it is under our control. So we say we control it. So we control this one, right? And okay, so now we go to write down everything in terms of the deformation of the field. So now I say alpha, the full derivative of j mu, is equal to this full derivative times, so this term here, and I had delta, I have delta phi here. So basically delta phi, we said, is taking phi to phi plus delta phi. Maybe I wasn't really clear on that. So the operation here, so delta phi means we take phi of x and add some variation. And we say this delta phi is equal to then alpha delta phi. So now I have to clear out again some mathematics here. Everything was the same as we proved delta operation. So we say delta operation is the variation, and then delta of phi is seen as some phi going to delta phi. This is the operation we do on the field, and then we write down this delta phi as some alpha of delta phi. It means that the whole operation is done by some arbitrary deformation times some infinitesimal parameters. So this infinitesimal parameter controls the strength of the transformation, and then delta phi just somehow preserve the arbitrary nature of it. So I just take out this alpha from this term, so my equation turns like this. Now I have this equation, I take everything on one side, so I would end it up in some. So now I have full derivative of two functions, so I can just take the derivative out because derivation is a linear operator, and this is equal to 0. So that would be seen as j mu minus the derivative of the Lagrangian with respect to the derivative of the fields times the deformation that we defined. So this deformation is something that we define. So now we have this term, which is the derivative of it is equal to 0. So now we just call this term in the parentheses j mu, or conserved current. So, and we know alpha j mu is equal to 0. That guarantees the conservation, right? These charges are carried by some jx, and jx is similar to the jx that we had in electrodynamic. If you remember, the external current always is labeled with j, the index j, and this j mu is somehow the current. So, and one more thing is that in most of the textbook, there is because this whole term is equal to 0, I can change the sign of it. So I can change one sign out. So this minus j mu, and this would be plus. So it is more convenient to write it like this. So j mu is equal to minus j mu. So this term depends on the deformation of the field. This term depends on Lagrangian response. So depends on what transformation I perform, what's the Lagrange of response here. So what's the Lagrange of Lagrangian response? So this is physics somehow, and this is math, because I choose what transformation to do, and my physics is determined by the Lagrangian. And we're going to see now, maybe it's not a very precise term that I say this is math, but this is physics. Lagrangian means how do we define Lagrangian, but this is also Lagrangian response, because we have this term here. The first term here is the Lagrangian response. Like, maybe I have to say this is math, and again this is physics. You know, I just like this argument, what's physics and what's mathematics, because some of them are just like arbitrary things that we define, but what put constraints on them is the Lagrangian form. And now it's a time to go to momentum energy conservation and the final argument, which is the electrical charges, or something similar to electrical charges. So now if I want to do energy and momentum conservation, energy, momentum, I want to do a space-time translation. So if I have a 4-dimensional or any dimension of a space-time, I want to just take, imagine that I have this box here. And imagine somehow I label this box here, and I have phi of x here, and I define a vector a mu, and this vector a mu is some multidimensional vector, but this is somehow my infinitesimal parameter. So my vector a mu is my infinitesimal parameter, and I translate the field into another point, so x plus a mu nu, or x plus a, right? And a is a form of vector. And there is something that we can work out the mathematics of it, right? So this is called a space-time translation. Space-time translation necessarily means phi at point x plus a is somehow phi of x plus the derivative with respect to infinitesimal parameter. So this is how we can expand, because the field is a scalar. So if we are just going into a neighborhood of it, that means that if we know the value of the neighborhood, we can work out the mathematics of these transformations, right? So I have this infinitesimal parameter here. So we know this is coming from Taylor expansion, right? And so I want to just like something. So if I have phi of x plus epsilon, then you might say I can somehow expand it in terms of phi of x0 plus some epsilon 0, the derivative of the phi at point x at the point of x0. So the precise mathematics is like that. So now, if I have such a transformation, both of my Lagrangian and my field should change in the same way, right? So my Lagrangian should translate like Lagrangian plus a mu, the muth derivative of Lagrangian. And Lagrangian is a scalar similar to phi. So same way it should translate. Phi of x should go to a mu, the derivative of phi. So what was the original Noether's theorem? Lx, or Lagrangian, was going to alpha, deformation of Lagrangian, and phi of x plus alpha, deformation of the field. So it is important to pay attention that the relationship between alpha and delta L is not an inner product. It is not an inner product. It is a scalar product. Scalar product. And we have to now go back to our expression and realize our expression is somehow an inner product. So this is inner product. So if we want to just correspond them together to find out those expressions, we need to somehow work out this inner product problem. So in terms of that, I am just using a mathematical tricks. Okay. So I say to get rid of this inner product, a mu and the mu's derivative. So let me write it down. A mu, imagine I have a mu. So in order to make the relationship between them like a scalar product, I should change their indexes. And the index is, it's arbitrary. You can choose which one to change. I can say it can be written as a mu. So instead of derivative mu, I write it down as derivative nu. So I change the component and then I use some delta operator here. So this delta operator is essentially now making the relationship between these two and a scalar. And then the delta goes inside with the rest of the thing. Okay, so now this is how we have to work out this math, because these indexes are important. If the indexes are similar, that doesn't mean that there's a scalar product. It is the inner product. Okay, so now I just write down the math. So the conserved current is equal to a nu, the mu's derivative. So I had the Lagrangian here, and then I had this delta mu nu. So I mean, just talk about it just right now. So for the case of Lagrangian, let's say the Lagrangian can be Lx alpha delta L can be written as Lx, or Lagrangian at point x, plus a nu, the mu's derivative, then delta mu nu. So let me say I just actually use the opposite one. I choose the other index for a. So I keep the a mu and I change the derivative to nu. Sorry about that. Sorry, I just changed the order. So that would be seen as Lagrangian plus a mu now you can correspond these two terms here. So term I, term double I. So I is equal to double I. That means alpha delta Lagrangian, which was basically alpha j mu. Sorry, which was basically alpha mu's derivative of j mu is equal to a mu, a nu times delta mu nu, the Lagrangian. So now I have this inner product here. So I can correspond my two infinitesimal parameters. And the good thing is that, sorry, this is the derivative. So this term is derivative. So this is a mu. Let's say a mu and then the new derivative and then the delta component. Like this. So now we have all the things in the right and correct order, right? And now we can just say the j mu is equal to delta mu nu Lagrangian. So now you might ask, what about this nu? This extra should also reflect here. So I mean, this is interesting that you see how we are just constructing one extra index. But that index is like a dummy index. The main index is this mu. The main index is this mu, and then we introduce the other index here, which is gonna come very handy right now, because we are gonna define energy tensor, which is the two index thing. So now we determine this j function here. This j function with some tricks is equal to the Lagrangian itself times some delta parameter. So this somehow can be obtained like this. So now I just write down J mu nu. So now I have, for my conserved current, I should also use this dummy index here. So now I have the derivative of the field times delta phi minus J mu. So I should also add this index nu here. So let me do it with the red color. And I should also add an index nu here for this term. And I should basically make this nu also in the same term. So now how to obtain this first term here. So now I have the second term. So I got the second term here. Okay. And then I go to the first term. So phi of x is going to be alpha delta phi, and then it could be written as the phi of x plus a nu, the mu's derivative. Then I have this delta mu nu of phi. So this is how I can just take these two terms equal to each other. So delta phi with an extra index nu can be seen as the mu's derivative with respect to delta mu nu of phi. Okay. And now, for convenient reason, I have to think of this mu as not the same thing inside of my expression. So my expression was like J mu nu is equal to the derivative of the Lagrangian with respect to the derivative of the field. Now we were supposed to put some delta phi with index nu here. So if we think of this red expression here as what we're going to replace down here, we realize that this mu inside of the first one is not necessarily the same with this yellow one that I'm highlighting here. So just for convenient reason, I just make them equal to like something like rho. So it is a dummy index because again it's summed up. So I just replace it with the rhoth derivative of some delta rho nu of phi, then minus the expression we found for the Lagrangian. So this is the expression we found for Lagrangian. This is the expression we found for delta phi. This is also J mu. And this is the first term that it is carried out by Lagrangian. So the final definition of energy momentum tensor is equal to something like this. Again, now let's calculate it. So the first term here can be calculated easily. We just calculated many times. So that would be the mu's derivative of phi. So T mu nu is equal to the derivative of phi times the rhoth component of delta rho nu phi minus delta mu nu Lagrangian. We have to be careful that this index should be matched. So there might be a possibility that sometimes we make a mistake. So maybe I made a mistake at somehow using mu and nu, but we have to be careful that they should make sense. When we are putting them equal, we cannot just like put all the indexes equal to 1. You know, there's some sort of techniques in the tensor analysis in math physics that it is useful here. But somehow this is how we drive the energy momentum tensor, and we're gonna see how different component of it is going to be energy and momentum. So I go to t0 0, so I put mu equal to 0 and nu equal to 0. And oh, by the way, so the mu's derivative of this energy momentum tensor is 0. So that's how we are sure that it is conserved, right? Everything is conserved somehow. Anything that it is constructed out of this integration. So if you have a kind of field which is conserved, which means the derivative of the boundaries is equal to the charge inside. So the theory is saying like that what it is coming inside of one particular region of a space-time should remain in that region. So we say rho plus so the time change in the so if we think of rho of x as the density of the current charges, this rho the time derivative of the rho plus those j's should be equal to 0. So anything that means that it is coming from one region of a space should somehow get out or be proportional to what's coming in as external charges. So if I calculate this t00, that would be the 0th derivative of phi, then I have the 0 derivative, and I have delta 00, which is going to be 1 of phi minus delta 00 of Lagrangian. And this is a very interesting term. This can be seen as the 0th derivative of phi times 0th derivative of phi minus Lagrangian, right? And the Lagrangian was what? The Lagrangian was the 0th derivative of the field. So we are now going back to the beginning of the session. We say Lagrangian. The kinetic term in Lagrangian has a Lorentzian signature, and then we're going to see how this minus signature is going to turn into plus when we're going into Hamiltonian. Minus 1 over 2 the x derivative of phi minus 1 over 2 m squared phi squared. So now I have this Lagrangian as this term here. So t00 is equal to this term here minus this whole thing. So this minus sign becomes plus, and this second minus sign is also becoming plus, and the final this only term 1 minus 1 over 2. So we're gonna ending up with something like this. So this is basically Hamiltonian. So this is the Hamiltonian of the field. And Hamiltonian have three terms here. So we have kinetic energy, a space deformation energy, and then self energy. So I call it self energy. This is like maybe you say a gradient energy. It's the energy stored in the elasticity of the field, or how it is distributed in a space. And this is somehow say kinetic energy. So kinetic energy is coming from the time change of the field. So it is like a speed of the field. And so yeah, let's say I wrote down Lagrangian as t minus v, then I can write down the energy as some kinetic term plus v. So that potential energy appears, but the Lorentzian signature should be in Lagrangian, because the Lagrangian is the one which is a scalar, not the Hamiltonian. Okay. And now the momentum component, the physical momentum component, is also can be extracted from this component, this energy momentum tensor. When we only have mu equal to 0, and then nu goes over 1, 2, and 3. So for momentum we have three momentums, but we need to fix one component, and that component is time. So we put it equal to 0. And then the different component t0i is going to be basically t0i and d3x. So these are like total momentum, and we want to show this total momentum is conserved. So basically the total momentum is the integral of so maybe I should reform it like this. The total momentum is equal to t0i d3x, right? And t0i based on the expression is the zeroth derivative of the field, and then I have this rhoth derivative of the field. Then I had some delta here, so I had this delta mu, and then instead I had this delta, and the upper component, the upper index should be rho, and the lower component should be I, right? This I is coming from this term here, so that means a spatial component of the phi minus delta of 0 and I. So this is beautiful because now it's going to be eliminated. It's going to be eliminated. So we don't have this term here. We don't have this term here. We only have the first term here. So the zeroth derivative of the field. So when we are talking about Lagrangian, the derivative of the Lagrangian with respect to the muth derivative of the Lagrangian was equal to muth derivative of the field. Like this is how we study Klein-Gordon real value. So this usually, for the case that mu is equal to 0, this term is equal to some field that we call it pi, and this pi is the equivalent of some momentum field. So this momentum field is just constructed from the original field. So the T0I is going to be pi times the ith derivative of the phi, because now we are just going into the first term here. So rho can be equal to I, which is 1, 2, and 3. So we basically, the I is ith derivative of the field. And P, total momentum, is equal to pi times the ith derivative of the field times d3x. So again, this is something intuitive to what we see. We can, sorry, there is also a minus sign here. For the convenient reason, they define pi as minus of the derivative of the field because of Euler-Lagrange equation. And if you look at the Euler-Lagrange equation, its minus sign somehow shows in the definition somehow to respect some of the symmetries in the equation. But in general, this is how we get the momentum information of the scalar field. So we can construct this total momentum. We're going to see this total momentum P over, so if I take this integration over some conserved volume or boundary, or volume with boundary condition. I mean, if I have a volume phi of x goes to phi x plus a, and imagine I have some boundary condition here, then this volume is somehow like isolated volume, and this total P is constant inside. So based on what we write as a conservation of those charges, then that means the integral on the boundary can be vanished, and then some charges are conserved. So these integrals are conserved integral. Now we're going to go to the final step, which is going to be the electrical charge or U1 symmetry. Again, this is a scalar particle. We still need more information. We need the information about fermions, and then we're going to talk about local gauge symmetry. So we are not still into local symmetry. We have two kinds of symmetries, global symmetry and then local, right? And these local symmetries are leading into gauge field. So gauge fields are those fields that are responsible to carry the electromagnetic forces or strong forces and so on. And these globals are somehow weaker conditions, but we're going to talk about right now U1 global symmetry. So U1 global symmetry. So U1 global symmetry means that, first of all, I need to go to the complex value scalar field. So the complex value of the scalar field is somehow something that has more information. Imagine that any complex number can be written as a plus ab, right? And technically, each complex number carries two numbers within itself, right? So it has more information. It just have double information. So it is very funny if you are probably, I was very struggling with this question, that how complex number goes into physics, even though they are not real or something, then I just realize, we all just realize, what does it mean that they are not real? Complex numbers are some numbers that they have higher dimensionality, so they are able to somehow perform very effectively, very good if you do circuits in physics. You know the miracle of using complex numbers in the equations makes everything very simple, but it is just not a technique. It means that it is a number that we reconstruct from real numbers, and in order to make more complete set of numbers, and the quantum is the art of somehow implementing those numbers in order to somehow go into the inner dimension information, because naturally they carry more information. So what imagine now I'm talking about a Klein-Gordon field, which the phi of it is complex values, and for some convenient reason, again, for knowing any complex number, you need two numbers. So you basically need two fields. For convenient reason, imagine phi and phi star are two independent fields. So the phi star is basically a minus ab. So phi is a plus ab. A. So if I imagine I write phi as a plus ib, phi star is basically going to be I minus AB, right? And then the idea is that if I have this two linear equation, then phi plus phi star divided by 2 is going to give me A. And then for the B, I can just subtract them. So divide them, phi minus phi star divided by 2 divided by I is going to give me B. At something like that. So instead of having A and B independently, I assume that I have two independent fields, phi and the phi star, and they are living somehow independent of each other at some point. So if I look at some value here, I am gonna read phi and phi star, and then the Lagrangian should be a scalar out of them. So it is convenient to write Lagrangian as the muth derivative of the phi and the muth derivative of phi star. Just basically there is a symmetry between phi and phi star. Phi and phi star should be similar in everything. There shouldn't be any difference between them. This is one of those symmetries. Minus m squared. So instead of phi squared, I just put phi star and phi. Again, all of these terms are symmetry. So now welcome to the complex value scalar field. Now we're going to see a very simple miracle here. Now we have some symmetry here, very global. I can take phi so I take my phi because it's a complex number, and then I multiply it by any phase which is global. So imagine I'm just multiplying my phi into a phase, and you realize that doesn't change my Lagrangian, right? Because now it's just so simple to see it doesn't change the Lagrangian because the two field behaves in a different way. So I have this phi goes to, imagine, exponential I alpha of the phi, then my phi star is going to go like minus I alpha of phi star. So the two transformations somehow cancel out in the Lagrangian. So neither of these terms are sensitive to this transformation, so the whole Lagrangian is invariant under this sort of transformation. So now I assume that there is some infinitesimal alpha, right? Because I can expand it. So phi goes to E I alpha of phi, and then I expand this exponential as identity plus I alpha, right? Times phi. So phi goes to phi plus I alpha phi. And then now you think about this as alpha delta phi, then I can just immediately identify delta phi is equal to I alpha. And then delta phi star in the same way is equal to minus I phi. Okay, but there is something interesting here, is that this Lagrangian doesn't have J mu. Do you remember we said if phi goes to phi plus alpha delta phi, Lagrangian goes to Lagrangian plus alpha delta Lagrangian. And there were two cases here. This delta Lagrangian can be 0, and this delta Lagrangian could be seen as the full derivative of some other function. So for the case of energy momentum, it was this. So it was the yellow case. But for this global phase transformation or U1 symmetry is the first case. So the Lagrangian doesn't overally change. Again, because energy momentum transformation was transformation in space-time. That means that we are going into another point. So Lagrangian would be the Lagrangian of some point plus something else. But now here, the Lagrangian is just simply doesn't change. So make everything so easy. In the J mu term, I don't have the large capital J mu term. So I have just the term, the derivative of the field. Sorry. So I just have the first term here times the deformation of the field. Well, however, here we have to add the two contribution of the field. So here I just only don't have one type of the field. That's the difference between the mathematics of the first real valued field. We only have phi. But when we are going to complex valued, we have phi and phi star. So we also had some contribution from the phi and phi star. So as we said, they should not be exactly phi and phi star should be exactly the same way as they behave. So in the charges, we have first term and the second term, and we just write it down as we calculated. We would be getting expression like this: the muth derivative of phi star phi, because the Lagrangian was this. So if I take the derivative of Lagrangian with respect to phi, I would get phi star. Sorry, the first term is phi star. And if I get the Lagrangian with respect to phi star, I would get the derivative in respect to phi. So the first term in the Noether current for the real valued field is going to be phi star. This phi star is coming from Lagrangian here. And then times phi, which is the deformation of the field. And the same thing for the phi star. Instead, we have this minus sign here because, as we said, phi and phi star showing different signs on the transformation. So that would be the muth derivative of phi times phi star. And now this is somehow symmetric. Maybe you say one of them has minus sign. It doesn't matter because we have the somehow we can transform it in a way that always flip the size. So this size is also here something that can be seen as symmetric. Really not the general argument, but here we get something into an expressional form, but it should have certain symmetry. Sometimes in some certain ways it should be anti-symmetric, and also anti-symmetric stuff similar to symmetric stuff. Okay. Now the zeroth component, so if I put mu equal to 0, the zeroth component of it would be J0 is equal to the integral, J is the current. It's going to be I, first derivative of phi times phi star minus phi star times the first derivative of the phi. And then I say, if I integrate this J0, that would give me the whole total electric charge. And this Q is going to be the equivalent version of electrical charges. So maybe you ask, where is this electrical, how did the electrical charges is coming into a way? The answer again is in the two component field here. So we have at each point, imagine that you have at the same time some phi and some phi star. And if you think about them, each phi can be seen as some a plus ab. And we know the complex number, the real part and the imaginary part, are somehow independent from each other. So when I say independent, I can maybe call a part positive particles and then b side negative particle. Again, we have to pay attention. This is not same positive and negative charges in electrical field and magnetic field, but we can think of it as any field has two kinds of information: how much of positive charges we have in one point and how much of the negative charges we have in some point. So if we somehow get into that symmetry, we realize that basically each point of the space-time has two fields, which determines how much positive and negative charges exist, because each of them are capable of carrying those information. So phi star and phi are capable of telling us some positive and negative entities. So apparently here, the first term here can be seen as positive. So maybe I should put the whole thing in the parentheses. So because this I is the derivative here. So this first term here can be seen as the field value times the derivation of the field value of the other type. And the second one is the same, some field value times the derivation of the other types of the values. So basically, these positive and negative charges are simply saying that when each of them is changing in time, so the muth derivative of phi is at each point is saying that how much phi is changing, and phi star is somehow saying that how much does already exist on that field. And the other term is the derivative of the phi star and then the phi. So that's how phi and phi star are capable of telling us how much balance, how much positive and negativeness are stored in one point. So this is how we get into this argument from the symmetry argument. So if you remember, we just started from Noether's theorem and we talk about U1. So this U1 is preserving this Lagrangian in the complex valued scalar field, and miraculously ending up in the concept of some charges. And again, by charges, you have to go to the dictionary. The word charges historically came from electric charges. Electrical charges were the first type of charges that we found. You're going to see, we're going to define more charges. We're going to define color charges, where the quark, which is responsible for a strong force. So charges is an extensive idea, but if we just think about charges only says about some balance of positive and negative value of the field, and it is coming from this symmetry. So now we are just ending this session, and I hope that in the next session we can go into the concept of quantization of this Klein-Gordon field, both of them, real valued and complex value. And we're going to see what's the meaning of quantization. And we said quantization basically means making them like operators and do bracket operations. So I hope that we're going to have the next session very soon. And thank you so much for watching this video.